Something just passed through our solar system. Not from here, not from the belt between Mars and Jupiter, not from the distant Kuiper belt beyond Neptune, from another star, July 1st, 2025, Atlas telescope in Rio Hurtado. Chile spots a dot moving through Sagittarius constellation. Speed, 221,000 kilometers per hour. Direction, straight into the inner solar system. Within hours, astronomers confirm the hyperbolic trajectory. This thing doesn't orbit our sun, it's passing through. One time only. Its name, 3I Atlas. The third interstellar visitor we've ever caught. The previous two, 1I Oumuamua in 2017, and 2I Borisov in 2019, gave us glimpses. But this one's different. This one's massive. And on October 3rd, 2025, spacecraft orbiting Mars got the closest view yet of anything from another star system. What they saw changes everything we thought we knew about interstellar objects. First discovery image shows a fuzzy dot, magnitude 18, faint. Most amateur telescopes wouldn't catch it. But professional surveys, they're built for this. Atlas had been scanning since June 5th torus, capturing pre-discovery images nobody noticed until the object was flagged. Why? It was crossing directly in front of the galactic center's dense star fields. A needle moving through a field of needles. Sam Dean, amateur astronomer, traced those early observations back through archived data, June 5th to June 29. 34 days of images sitting in servers, unnoticed, while 3I Atlas closed in at 61 kilometers per second. Zwicky Transient Facility at Palomar Observatory found even earlier captures, June 14th. That's the earliest confirmed sighting. At that moment, 3I Atlas was 4.51 astronomical units from the Sun, 3.50 from Earth, already active, already glowing, already releasing gas into the void. Within 48 hours of official discovery, 3 observatories confirmed the coma. Deep Random Survey in Chile, Lowell Discovery Telescope in Arizona, Canada, France, Hawaii Telescope at Mauna Kea all showed the same thing, a marginal halo, 3 arc-seconds of tail-like elongation. Not an asteroid, a comet. David Jewett and Jane Liu at Nordic Optical Telescope, July 2nd, confirmed it was clearly active with diffuse appearance. The Minor Planet Center announced 3I/Atlas that same day. 122 observations from 31 observatories. The designation 3I third interstellar object confirmed. Also C/2025, N1 Atlas, non-periodic comet. It's never coming back. If you value documented interstellar exploration and cutting-edge astronomical observation like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual. Using sources from the European Space Agency's ExoMars mission data, released October 7th, 2025, NASA's Hubble Space Telescope observations, published August 7th, 2025, and James Webb Space Telescope NIR Spec Campaign results from the Archive preprint server dated August 25th, 2025, paper reference 2508.18209. These are peer-reviewed and mission-verified sources directly from the instruments that captured this data. Now back to the information. The size question hit immediately. Early brightness calculations suggested 10 to 20 kilometers diameter. Too big, way too big. That would make it 1,000 times more massive than 2I Borisov. You don't find giant interstellar objects before finding thousands of smaller ones. The math doesn't work, but the brightness was real. Something was glowing. Hubble space. Telescope turned its mirror toward 3I Atlas on July 21st, 2025. Distance 446 million kilometers from Earth. 3.8 astronomical units from the Sun. Exposure tracking the comet's hyperbolic path. Background stars streaking across the frame. The image revealed a teardrop-shaped cocoon of dust. Not a tail, not yet. Just a compact glow, 4,000 kilometers across, extending modestly toward the Sun. The nucleus itself, invisible. Too small for even Hubble's resolution. But the constraints tightened. Upper limit, 5.6 kilometers diameter. Lower limit, 440 meters. The most likely size, under 1 kilometer. Similar to 2I Borisov, but here's the problem. The glow wasn't just from a tiny nucleus. The brightness implied something bigger. Spherex Space Observatory, August 8th through 12th, observed 3I Atlas at near-infrared wavelengths, 3.0 micrometers, 4.26 micrometers, 4.7 micrometers. Water, carbon dioxide, carbon monoxide emission lines, water, undetected, carbon monoxide, undetected, carbon dioxide, blazing, a symmetric cloud extending at least 348,000 kilometers. That's 2.3 times the Earth-Moon distance. Mass loss rate, 70 kilograms per second of carbon dioxide. Water upper limit, 4.5 kilograms per second. The spheric's brightness at 1 micrometer wavelength suggested a nucleus diameter of 46 kilometers. If that's solid, if 99% of the brightness comes from icy fragments in the coma, the nucleus drops to 5 kilometers. Still huge. Still 1,000 times the mass of 2I Borisov. Avi Loeb at Harvard calculated the implications. For a 46-kilometer diameter with 4% albedo, typical for Kuiper belt objects, the mass hits 33 billion tons, 33 quadrillion kilograms. That's the mass of a small mountain range compressed into a comet. This creates an anomaly. Given the limited reservoir of rocky material in interstellar space, we should have discovered 100,000 objects the size of Oumuamua before finding 3 I Atlas. But we only detected 2 interstellar objects previously. James Webb Space Telescope, August 6th, 2025, 3.32 astronomical units from the Sun. NIR spec instrument, near-infrared spectrograph, 0.6 to 5.3 micrometers. The spectral images came back. Carbon dioxide dominated coma, enhanced outgassing in the sunward direction. Water vapor, present but weak. Carbon monoxide, trace amounts. Carbonyl sulfide, detected. Water ice, absorption features visible. Dust, scattered throughout. The carbon dioxide to water mixing ratio hit 7.6 plus or minus 0.3, among the highest ever observed in any comet. 4.5 sigma above the trend for long period and Jupiter family comets. Only one outlier in solar system comets shows similar ratios, C/2016 R2. What does this mean? 2 possibilities. First, 3 I Atlas contains ices exposed to higher levels of radiation than solar system comets, cosmic rays bombarding the surface for billions of years in interstellar space. Or second, it formed close to the carbon dioxide ice line in its parent protoplanetary disk. That's the boundary where carbon dioxide freezes in a forming solar system. Different from our system's ice line, different star, different chemistry. Matthew Hopkins, Oxford astronomer, defended his doctoral thesis 1 week before 3 I Atlas was discovered. His thesis, the Ototahi Oxford model, predicted the properties of interstellar objects based on galactic populations. July 1st, Discovery Day, he woke to messages. 3I exclamation, 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 exclamation. His model predicted objects from the Milky Way's thick disk should be old, 7.6 to 14 billion years old with 68% confidence. The solar system is 4.6 billion years old. 3I Atlas might predate everything we've ever touched. Chris Lintott, co-author, BBC Sky at Night presenter, stated there's a 2/3 chance this comet is older than the solar system. It's been drifting through interstellar space ever since. The trajectory tells the story. Hyperbolic excess velocity, broken into galactic coordinates. U component, negative 51.0 kilometers per second. Moving away from galactic center, V component aligned with galactic rotation. W component, positive 18.5 kilometers per second. Moving upward through the galactic plane. That W velocity is high. Most nearby stars don't move vertically that fast. 3 I Atlas follows a tilted orbit around the Milky Way, either thin disk or thick disk population. The thick disk consists of older stars, lower metallicity, ancient formation, independent analysis by Astor Taylor and Daryl Seligman. July 2025, estimated 3 to 11 billion years old. Broad agreement, this thing is old. September 2025 study by Yi Yang. Guo found 3 I Atlas may have passed within 1 parsec, 3.3 light years. Of 25 known stars in the past 10 million years, close encounters, gravitational nudges. Each one changed its trajectory slightly. Each one added velocity through gravitational slingshot effect. You can't trace it back to a parent star. Too many interactions. Too much time. It's been wandering too long. The comet continued inbound. July 21st, Hubble observations. August 6th, Webb observations. August 8th through 12th, Sphere-X observations. August 21st, Very Large Telescope in Chile detected cyanide and nickel in the coma. Cyanide gas, hydrogen cyanide, production rate measured by James Clerk Maxwell Telescope on September 7th. 1.5 plus or minus 0.5 times 10 to the 25th molecules per second. September 14th. Production climbed to 4.5 plus or minus 1.9 times 10 to the 25th molecules per second. 2 kilograms per second of cyanide. The coma on September 15th stretched 180,000 kilometers across asymmetric elongated along the anti-solar direction. Dust tail visible, 50 arc seconds, roughly 100,000 kilometers. Apparent magnitude 14.2. Mars approach began October 3rd, 2025. Closest approach to the red planet. Distance 30 million kilometers, 18.6 million miles. That's the closest any spacecraft would get. ESA's ExoMars Trace Gas Orbiter and Mars Express, both orbiting Mars since 2016 and 2003 respectively, turned their instruments toward the interstellar visitor. This was the moment. The closest view yet from any spacecraft. ExoMars Trace Gas Orbiter, equipped with color and stereo surface imaging system, CASes, designed to photograph Mars' surface from a few hundred to a few thousand kilometers below. Not designed for faint, distant targets. Nick Thomas, principal investigator, stated this was a very challenging observation for the instrument. The comet is around 10,000 to 100,000 times fainter than our usual target. 5-second exposures, stacked to build signal. The camera's angular resolution, 11.36 microradians, 2.34 arcseconds per pixel. At 30 million kilometers distance, that translates to 340 kilometers per pixel. The expected nucleus diameter ranges between 5 kilometers minimum, based on mass calculations, and 46 kilometers maximum from Sphere-X brightness data. Even the largest estimate is smaller than a single pixel. The images came back October 7th. Animation released by ESA. A slightly fuzzy white dot moving downward near the center of the frame. Stars streaking in the background because CASes tracked the comet. That fuzzy dot is the coma, a few thousand kilometers across. Gas and dust cloud. The nucleus itself, indistinguishable from the coma at this distance, like trying to spot a cell phone on the moon from Earth. Impossible. But the coma, clearly visible. The brightness drops quickly with distance from the nucleus. The full extent couldn't be measured because the faint outer regions fade into image noise. Mars Express also attempted observations with high-resolution stereo camera. Exposure time, 0.5 seconds. Maximum limit for Mars Express, too short. The comet didn't appear in those images. Scientists will stack multiple Mars Express frames to see if adding them reveals the faint signal. Spectrometers attempted measurements. Mars Express, Omega, and SpyCam. ExoMars, TGO, Nomad. Whether the coma was bright enough for spectral characterization remains uncertain. Analysis ongoing. Colin Wilson, Mars Express and ExoMars project scientist at ESA, stated, though our Mars orbiters continue to make impressive contributions to Mars science. It's always extra exciting to see them responding to unexpected situations like this one. I look forward to seeing what the data reveals following further analysis. The CASes image shows a bright glow approximately 680 kilometers wide, about twice the diameter of bright background stars in the same frame. Point sources. The comet's glow is extended. Avi Loeb analyzed the CASes surface brightness profile. At 30 million kilometers, the CASes primary mirror, 13.5 centimeters diameter, has a surface area 300 times smaller than Hubble's mirror. The detection of glow out to 680 kilometers matches the Hubble surface brightness profile, amplified by the increase in sunlight brightness near Mars compared to where 3I Atlas was during Hubble observations. This suggests no major increase in outgassing over the 3 months between observations. Steady state activity. The Sphere-X carbon dioxide plume, 348,000 kilometers radius E, extends far beyond what CASes could detect. That plume is spherically symmetric, confined by ram pressure from solar wind. The Hubble fuzz showed mild extension toward the Sun, length to width ratio about 10 on the scale of thousands of kilometers. The CASes sideway view, nearly perpendicular to the 3I Atlas Sun axis, confirms this geometry. The brightest region around the nucleus is all CASes captured. The lower surface brightness envelope visible in Hubble missed entirely. NASA's Mars Reconnaissance Orbiter also observed 3I Atlas. High-rise camera, 0.5 meter aperture, resolution at 30 million kilometers, 30 kilometers per pixel. Better than CASes, but still not enough to resolve the nucleus directly. The data hasn't been released. NASA, government shutdown in October 2025, delayed publication. Colin Wilson at ESA mentioned the NASA data is seemingly quite good. Results pending. NASA's Curiosity and Perseverance rovers, both on Mars' surface, attempted observations from ground level, looking up at the Martian night sky. Whether they captured the comet remains unconfirmed. NASA hasn't released those results either. What do the Mars observations reveal about 3I Atlas' true nature? The consistent brightness and coma structure across 3 months of observations, from Hubble in July to CASes in October, shows stable outgassing. No major outbursts detected, no fragmentation events. 2. I fragmented. Comets often do as they heat near the sun. 3. I Atlas, stable. This suggests either a robust nucleus or an unusual composition that resists thermal stress. The carbon dioxide dominance is key. Normal comets are water-rich, ice H2O. 3I Atlas barely emits water vapor. Carbon dioxide drives the activity. At 3.32 astronomical units from the sun, when Webb observed it, the temperature is too low for efficient water sublimation. Water ice line in the solar system sits around 2.5 astronomical units. 3I Atlas was outside that, but carbon dioxide sublimates at lower temperatures. It activates earlier. The high carbon dioxide to water ratio, 7.6 to 1, implies the comet's formation environment was carbon dioxide rich, either high radiation exposure in its birth system or formation near the carbon dioxide ice line. The old age estimate, potentially 7 billion years or more, supports the radiation hypothesis. If 3I Atlas has been drifting through interstellar space for 3 billion years longer than our solar system has existed, cosmic rays have been sandblasting its surface, radiation processing, altering the ice chemistry, depleting water, concentrating carbon dioxide. Studies of Kuiper Belt objects show similar effects on much shorter timescales. 3 billion years of exposure could produce extreme alterations. The cyanide and nickel detections by Very Large Telescope match solar system comet concentrations. That's surprising. If 3I Atlas is so chemically different in water versus carbon dioxide, why are trace elements similar? It suggests the fundamental building blocks, the refractory materials, the metals, the organic compounds, are universal. Different star systems produce similar raw materials. The ice mixture varies based on formation distance from the star and radiation environment, but the core chemistry stays constant. The size mystery persists. If the nucleus is truly 5 to 46 kilometers diameter, that's enormous for an interstellar object. Avi Loeb's anomaly argument holds weight. We shouldn't see something this big before finding thousands of smaller objects, unless 3I Atlas isn't random, unless its trajectory was influenced by something. The alignment with the solar system's orbital plane is a 1 in 500 coincidence for random occurrence. The path brings it deep into the inner solar system, passing Mars at 0.19 astronomical units, separation on October 3rd. Perihelion at 1.36 astronomical units on October 29th or 30th. That's between Earth's orbit and Mars' orbit. Some researchers, including Loeb, entertain the possibility that 3I Atlas could be artificial, an interstellar probe, technology. But the spectroscopic data from Webb and SphereX shows clear cometary composition. Carbon dioxide ice, water ice, carbonyl sulfide, cyanide, nickel, dust. These are natural materials. The outgassing follows physical sublimation laws. The velocity of ejected material, 0.44 kilometers per second, matches thermal escape from heating ice. No propulsion signatures, no geometric structures visible in images, just a fuzzy comet. The minimum mass calculation, based on non-gravitational acceleration, gives 33 billion tons. If you eject 150 kilograms per second at 0.44 kilometers per second, the rocket effect produces acceleration. 3I Atlas shows less than 15 meters per day, squared non-gravitational acceleration despite significant outgassing. That requires enormous mass to resist the push, 33 quadrillion kilograms minimum. For a nucleus diameter between 5 and 46 kilometers, the density falls within the range of known comets, porous ice and rock. Nothing anomalous about the density, just the absolute scale. October 29th, 2025, perihelion, closest approach to the Sun, 1.36 astronomical units, 203 million kilometers. The comet disappears behind the Sun from Earth's perspective. Solar conjunction on October 21st, 8 days before perihelion. Unobservable from Earth for weeks. Mars orbiters provided the last close view before the Sun's glare blocked everything. By early December, 3I Atlas will reemerge on the other side of the Sun, visible again from Earth, but farther away, speeding outward, heading for Jupiter. ESA's JUICE spacecraft, Jupiter Icy Moons Explorer, en route to Jupiter, will observe 3I Atlas in November 2025. Multiple instruments, cameras, spectrometers, particle sensor, coordination with NASA's Europa Clipper mission considered, twin ultraviolet spectrographs, one on each spacecraft. JUICE sits close to the Sun, using its main high-gain antenna as a heat shield. Communications limited to medium-gain antenna. Slow data rate, far from Earth. On the opposite side of the Sun, data from JUICE's observations won't arrive until February 2026. The Juno spacecraft orbiting Jupiter might observe 3I Atlas when it passes close to Jupiter in March 2026. 0.36 astronomical units. Separation, 54 million kilometers. But Juno is low on fuel. Engine issues. Redirecting to 3I Atlas introduces risk to the primary mission. Unlikely. NASA's Psyche spacecraft passed 0.302 astronomical units, 45 million kilometers, from 3I Atlas on September 4th, 2025. No attempt to observe. Too risky for the mission. Same for Jupiter Icy Moon's Explorer during its November pass. Primary mission takes priority. After Jupiter, 3I Atlas exits the solar system. Forever. The hyperbolic trajectory doesn't close. Escape velocity achieved. It came from the direction of Sagittarius, from the galactic center's direction, and it will leave in a different direction, deflected by the sun's gravity. Where it goes, we'll never know. Deep space, wandering between stars, another few billion years of drift. Maybe it passes close to another star. Maybe that star has planets. Maybe observers there see it too. Or maybe it drifts in the dark, unobserved, for eternity. The legacy of the Mars observations isn't just the images, it's the coordination. 2 spacecraft built for planetary science, repurposed on short notice to observe an interstellar visitor. The Cassis camera, designed for Martian geology, capturing something from another star. The spectrometers, attempting measurements at the edge of their sensitivity. This is adaptive astronomy, using what we have, where we have it. When opportunity arrives, no time to build a dedicated mission. 3I Atlas moves too fast. By the time you design, fund, build, and launch a probe, the target is gone. You use existing assets, you improvise, you capture what you can. The data from ExoMars Trace Gas Orbiter will be analyzed for years. The spectroscopy, if successful, could reveal isotope ratios. Carbon-13 to carbon-12, oxygen-18 to oxygen-16, deuterium to hydrogen. These ratios vary depending on where and when an object formed. Our solar system has characteristic ratios from the protoplanetary disk 4.6 billion years ago. 3. I-Atlas formed somewhere else, someone else, its isotopes should differ. If the NOMAD spectrometer on ExoMars TGO caught enough signal, those ratios could be extracted. That would tell us about the chemistry of another star's planetary system. Direct measurement, not inference from distant spectroscopy of exoplanet atmospheres. An actual sample, passing through, analyzed up close. The October 3rd observations mark the closest any human-built instrument has been to an interstellar object while it's active. Oumuamua was discovered outbound, already past the sun, inactive, tumbling. No coma, no outgassing visible. 2Y Borisov, observed extensively during its 2019 pass, but never this close by a spacecraft. Ground-based telescopes only. 3I Atlas, caught by Mars orbiters at 30 million kilometers during peak approach. Active, outgassing, coma fully formed. This is the data set. This is what we have to understand interstellar visitors. What we know now. 3. I-Atlas is likely 5 to 46 kilometers diameter. It's at least 33 billion tons. It's carbon dioxide, rich, water poor. It's old, possibly 7 to 14 billion years. It came from the Milky Way's thick disk. It's been wandering for billions of years, nudged by countless stars, accelerated by gravitational slingshots. It's stable, no fragmentation, steady outgassing. It contains cyanide, nickel, carbonyl sulfide, traces of water vapor, traces of carbon monoxide, and lots of dust. Its coma extends thousands of kilometers. Its carbon dioxide plume hundreds of thousands of kilometers. Its nucleus is too small to resolve directly, even with the best cameras we have at Mars orbit. But it's there. Solid. Icy. Rocky. Ancient. What we don't know, the exact size, the exact mass, the exact composition of the nucleus interior, whether the surface is uniform or varied, whether the high carbon dioxide is intrinsic or radiation processed, how much water ice is buried beneath the carbon dioxide, rich crust, whether the object will fragment as it rounds the sun, whether it will produce outbursts, whether its rotation is stable or chaotic, where it formed, which star, when it was ejected, how many close encounters it had with other stars during its journey, whether it's typical of interstellar comets or an outlier. The Mars observations provided the closest view yet, but it's still a fuzzy dot, a few thousand kilometers of coma reduced to pixels. The nucleus, invisible? We need better instruments, closer passes, or we wait for the next one. The Vera Rubin Observatory, beginning operations now, should find 5 to 50 interstellar objects over the next decade. That's the prediction. 3, I-Atlas suggests the optimistic end of that range. Maybe 50, maybe more. Each one will be different. Each one a sample from a different star system. Each one carrying information about planet formation in another part of the galaxy. Interstellar comets are time capsules. They formed around stars billions of years ago, stars that might be gone now. Some of those stars could have exploded as supernovae. Some could have been consumed by black holes. Some could have been gravitationally ejected from the galaxy entirely. But the comets they birthed still drift, still carry the chemical signature of those ancient systems. 3I Atlas might be from a star that died 2 billion years ago. We'll never know. But the comet remembers. The isotopes remember. The ice chemistry remembers. A final data point emerged mid-October. The trajectory analysis based on 5 months of observations. May 15th through September 23rd, 227 observatories, thousands of data points. The non-gravitational acceleration, less than 15 meters per day squared. That's tiny. For the observed mass loss of 150 kilograms per second, the comet should accelerate more. Rocket effect, push from the ejected gas. But it doesn't. The mass must be enormous to resist that push. Either the nucleus is 46 kilometers across, or it's much denser than normal comets, or we're underestimating the mass loss rate. The Mars Reconnaissance Orbiter observations, when released, might resolve this. High-rise brightness measurements at 30 million kilometers, combined with known solar flux at that distance, could separate nucleus brightness from coma brightness. That would tighten the size estimate. The coma brightness distribution in the CAS's images, when fully analyzed, will give the dust density profile. That constrains the dust production rate. The spectrometer data from NOMAD, Omega, and SPICAM, if bright enough, will give the gas composition at 30 million kilometers from Mars, which is 3.32 astronomical units from the Sun at that time. The distance, when Webb observed, same distance, enables direct comparison. Did the composition change? Did the carbon dioxide to water ratio shift? Did new volatiles appear? Sulfur compounds? Ammonia? Methanol? Hubble will observe 3 I-Atlas again in November, performing ultraviolet spectroscopy. UV lines reveal the gas emission composition and sulfur to oxygen ratio. Sulfur chemistry tells us about the original nebula where the comet formed. High sulfur means formation in a sulfur-rich region, possibly near a young star with vigorous stellar wind. Low sulfur means formation in a quieter environment. Oxygen isotopes, if measurable, will compare directly to solar system values. Every measurement narrows the possibilities. Webb will observe again in December, after perihelion. Post-perihelion observations show the comet after maximum heating, after peak activity. Does it survive intact? Does it fragment? Does the activity drop rapidly or slowly? The post-perihelion light curve shape reveals the volatile distribution in the nucleus. If volatiles are concentrated in the outer layers, activity drops fast. If they're distributed throughout, activity decays slowly as the comet cools. By March 2026, 3I Atlas will be beyond Jupiter, receding into the outer solar system at 68 kilometers per second relative to the Sun, visible only to the largest telescopes. Ground-based observatories will track it as long as possible, months, maybe a year, until it fades below detection threshold. Magnitude 20, magnitude 25, gone, back into interstellar space, another dot among stars. But the data remains, the images, the spectra, the brightness curves, the isotope ratios if we got them. The comet's brief passage through our neighborhood handed us information we can't get any other way. We can't visit other star systems. Not yet, not for centuries. But occasionally, rarely, pieces of other star systems visit us. Oumuamua taught us interstellar objects exist and move fast. 2, Borisov taught us interstellar comets look similar to solar system comets. 3, I-Atlas teaches us they vary, wildly. Ancient, massive, carbon dioxide rich, stable, fast, old. This is the diversity. This is the galaxy. Trillions of comets, each one different. Wandering the space between stars. The closest view from Mars' orbit revealed a coma. Steady, extended, dust and gas, carbon dioxide dominant, no nucleus detail, too small, too far. But the brightness, the stability, the chemistry, the trajectory, all confirmed. This is a real comet from a real star system, from a real ancient time in galactic history. 7 billion years ago, when 3I Atlas might have formed, the Milky Way looked different. The Sun didn't exist yet. Our solar system wouldn't form for another 3 billion years. Earth was 3 billion years away from existence. Life, 4 billion years from emerging. And yet, somewhere in the thick disk of the galaxy, around an old metal poor star, Ice and rock coalesced. A comet formed. Gravity from a giant planet, or a close pass with a neighboring star. Flung it outward. Escape velocity. Into the dark. It drifted. For billions of years, passing star after star, nudged by gravity, accelerated by slingshots, wandering, and on July 1st, 2025, it entered our solar system. A telescope in Chile caught it. Observatories around the world confirmed it. Hubble imaged it. Webb analyzed it. SphereX mapped its carbon dioxide plume. Mars orbiters captured it at closest approach, 30 million kilometers, 18.6 million miles, a fuzzy white dot in the Martian sky. The most ancient visitor we've ever seen, the most massive, the most mysterious. And on October 3rd, 2025, for a few hours, we got the closest look any spacecraft will ever get at this traveler from another world. What it reveals? We're still learning. What it means? We're still figuring out. But one thing is certain. We're not alone in making comets. Other stars do too. And sometimes, rarely, those comets come to us, carrying messages in ice, stories in isotopes, secrets in carbon dioxide ratios. 3I Atlas passed through. The Mars orbiters watched. The data is in, and now we know a little more than before about how planets form around distant stars, about how comets drift through the galaxy, about how old ice can travel, about what's out there in the space between stars, waiting to be discovered. The November 2025 observations by JUICE, pending until February 2026, data returns Stewart, might show 3I Atlas at peak activity post-perihelion. The December Hubble UV spectroscopy will test the sulfur-oxygen ratio. The post-perihelion Webb observations will measure the cooling curve. Every data point adds to the story. Every spectrum refines the model. Every measurement brings us closer to understanding not just 3I Atlas, but all interstellar visitors. The next one, and the next. 5 to 50 over the next decade. The Vera Rubin Observatory scanning, Atlas watching, Zwicky Transient Facility capturing. Sooner or later, another dot will appear. Moving wrong, too fast, hyperbolic, and the cycle begins again. Discovery, confirmation, observation, analysis, learning. 3. Atlas, the massive wanderer from the thick disk, 7 billion years old, 5 to 46 kilometers across, 33 billion tons minimum, carbon dioxide rich, stable, fast, ancient, observed by Mars orbiters on October 3rd at 30 million kilometers. Closest view yet from any spacecraft to revealed to be exactly what the old models predicted, and nothing like anything we expected. A comet from another time, another place, another star, passing through, once, now gone. Data remains.